So question 2 says the figure shows a counter shaft subjected to gear forces as indicated. The bevel gear forces are given by Fd equals so and so. So they have mentioned it has an I component, J component and K component. I refers to the force in x-axis, J refers to the force in y-axis and K refers to the force in z-axis. The design of the shaft is such that the bearing at O is the only one that can take axial loads. So in the figure we can see that there's a counter shaft. It has two bearings O and B and it has two gears A and D. So as we can see there is force mentioned here and it is given by this equation for the bevel gear at D. And it's also mentioned that only bearing O has axial loads, that it can only take axial loads. Bearing B cannot take axial loads. We are asked to draw appropriate normal bending moment and torque diagrams for the shaft and also to identify possible critical section and the corresponding internal forces. So let's start with the free body diagram. So draw free body diagram. So in this question, we can draw the shaft in two different ways, or we can draw two different free body diagrams. One could be just one diagram representing all the three axes, or we can draw two separate free body diagrams showing two axes at a time. So we will go through both methods. So first I'm going to do the three axis method. So I'm going to draw the shaft as a straight line. I'm going to mention here how the axis is going to be. This is x-axis positive, y-axis positive, and z-axis positive. So let me mark this as point O. This is point A, point B, and point D. So let's go to the location here. What do we have? We have a bearing, and a bearing typically will have reaction forces in all directions unless it is specifically mentioned that it doesn't have in direction. So in our case we have at O we have all three reactions ROX, ROY and ROZ. So let's assume these to be positive and we can mention in the diagram this is ROX, this is ROY and ROZ. So those are the forces at point O. Now moving on to point A, we have force applied on the gear and the values are present here. So let's see what is there in the x-axis. In x-axis we have 1.05 kilonewton but in the direction opposite to the direction of the axis. In the y-axis we have a certain value which is positive and in z-axis we have a force which is in the opposite direction. So this will be negative, this will be negative and this will be positive. So FAX, let's mention it as FAX, it is this way, which is negative direction. FAY is positive, and FAZ is the other way, so this way, FAZ. Now another component that would be generated here would be moment, because this force is applied at a location away from the shaft. So what happens is this force is applied on this gear. This x-axis force would create a moment about y-axis, because if you shift this y-axis to this gear over here, you can see that this x-axis is going to cause clockwise momentum about y-axis. So we will have a momentum about y-axis and we can mention this as momentum AY, okay, due to the force x, f of x. Okay, Fa of x. Now let's look at the other force, which is Fay. This is also going to create a momentum about the shaft axis, which is the x-axis. So it is also a clockwise moment about x-axis. So we will draw this as clockwise moment, and we can write it as max. So actually I have made a mistake here. I drew this counterclockwise. So let me just erase it. So I drew this opposite. So the direction was clockwise as well. MAY. Okay. So MAX and MAY. X is the axis about which it is occurring. So MAY is about the y-axis, MAX is about the x-axis. So the force that is creating MAX again is the force in y direction, and the force that is creating the moment in y-axis about y-axis is in x-axis. Now let's move on to point B. As mentioned in the question, the bearing O is the only one that can take axial load. So there is no force Bx. So we will just have RO, I mean RBy and RBz. So now I'm assuming them to be positive. And now let's move on to point D. We have three forces, Fx, Fy and Fz. Fx and Fy are negative direction. Fz is in the same direction of the axis. So that will be positive. So F dx, F dy, and we have F dz, which is positive. Now again, this is applied at a location away from the shaft. So we can have two moments at least. So f of x is going to create a moment about the z-axis. Because if you shift the z-axis here, this load is going to rotate about that axis. It's trying to make this gear rotate about that axis. Similarly, Fz is going to rotate about the x-axis, the shaft axis. So we have again two moments. In this case, it is going to be counterclockwise, and even this is going to rotate counterclockwise. So we'll have to draw it counterclockwise, so this way, and we can mention it as mdz, and again it is counterclockwise here, and we can mention this as mdx. So those are all the forces and moments in the free body diagram. The last thing would be to mention the distance between each point. This is 450 and the last one is 400. So this is the free body diagram in 3 dimensions. Now it looks really complex and it might take some time to identify the forces accurately in this free body diagram. So we have another option to split this into two separate free body diagrams. So I'll mention this as option 2. This is option 1. So in option 2, I'm going to draw the shaft in the same manner. I'm going to mention just x, y axis, plot the points similarly, which is O, A, B and D. And this time I'll only mention the reactions and moments in x and y axis. So this one is ROX and we have ROY. At A we have FAX in the negative direction and we have FAY. We will not write any of the Z components. So these are the forces. We'll start with the forces and then move on to the moments. At D we have Fdx and Fdy, which is also negative. Okay, now I'll go to the moments. So as mentioned earlier, about the x-axis we have moment max, and about the y-axis as well we have a moment which is clockwise. Clockwise, both are clockwise, so m a y. And in this as well we have moment about x-axis mdx, but we don't have any moment about y-axis. Again, why we don't have moment about y-axis? This force is in line with the shaft. So what happens is we don't have a perpendicular distance away from the shaft. This is in the same line of the force. If you have a perpendicular distance from the force, then we can consider moment to occur in that location. Similarly here, the z-axis force is not creating any moment because it is in line with the axis of the shaft. So there is no perpendicular distance between this force and this. But let's say in this case, we have this as the force. The perpendicular distance is the radius of the gear. Same thing goes in this case. So now this free body diagram looks less complex. The last part would be to mention the distance again. Okay. Now the second free body diagram for option 2 would look similar. It has the x z axis. Prefer to keep x in the same line because that way it will be easy to visualize the difference between the y-axis and the z-axis. So let's mention the points again: O, A, B, and D. And this again we are repeating the forces ROX, and this time it will be ROZ. And here we have FAZ, but it is in the negative direction. So I'll go back and fix it. So this is FAZ, and what else do we have? We have FAX this way, and again we can mention that there is this clockwise moment here, MAX. We don't have any moment about the z-axis. And for the location B, we have FBZ. I forgot to mention the force here on the other diagram. It was FBY. And at location D, we have uh, this one is positive, so it has to be this way, FDZ. And this is negative, FDX. And again, we have the moment MDX, and we have the moment counterclockwise as well. You can mention it as MDZ. Okay, and the distance 550, 450, and 400. Okay, so those are the ways we can draw the free body diagram. Whichever is comfortable for you, you can use. The 3D one compresses it into one figure, but 2D option has to be two different figures with repeating constraints. So now that we have drawn the free body diagram, let's write down what is known to us. So first of all, forces uh, FAX, it is given to us, and the value is negative 1.05 kilonewton. That's because the direction is against the positive x. And FAY is equal to 4 kilonewton, that is positive, and FAZ is equal to minus 1.47 kilonewtons. So these are known. Also at location F, dx is equal to, we can mention it as minus 0.242 f, because this is for the x-axis. So it is minus 0.242 f. F dy would be minus 0.242 f as well, and f dz is equal to 0.94 f. These are all in newtons. Okay, now after this we also know the moment. We can find it. So max, may, mdx, and mdz. So I think that should cover everything from the knowns. So max, may, mdz, mdx. So max would be uh, about the x-axis. So it should be force in y times the perpendicular distance, which is the radius of the gear. So 4 times 250. This should be 4 times 250, which is equal to 1000. But again, this moment is clockwise. MAY, it is caused due to the x-axis force about y-axis. So that would be 1.05 times 250 as well. So that's going to be equal to 262.5, and this is also clockwise. MDX and MDZ. MDX would be uh, the force in Z axis, which is 0.94. We already mentioned 0.94 F. So 0.94 F times the half of 375, which should be 187.5. Okay, so 187.5, and this should be 0.242 F times the same. So again, we don't know what is F at the moment. So we'll just leave it as F, and these distances are all in millimeters. So the value that we get over here is kilonewton millimeters, and the ones above are Newton and kilonewton respectively. This is also newtons. Okay. So these are all the knowns. Let's mention what are the unknowns. Unknowns include, going back to this figure, we have ROX, ROY, ROZ. These are unknown. RBY, RBZ are unknown. And one more thing that is unknown is the F. We don't know what is this F in here. So the unknowns are ROX, ROY, ROZ, RBY, RBZ, and F. So we have 6 unknowns, so we will require 6 equations. So we will start by applying, which is the step 2, applying equations of motion. Equations of motion. So for the 3D problem, how many equations of motion we have? We have the summation of force in x, summation of force in y, summation of force in z, moment about x, moment about y, and moment about z. So we have 6 equations and we need to solve for 6 unknowns. So the solution is solvable, hence we can continue with the steps. So let's start with summation of force in x equals 0. Always mention the direction that you are assuming positive. So summation of force in x, if we go back to the free body diagram, we have in here ROX, which is positive, we have assumed, FAX, which is negative. At B we don't have any x component, and at D we have FDX, which is negative. So it's going to be ROX minus FAX minus FDX. So ROX minus FAX minus FDX is equal to 0. So from this we can find what is ROX. Minus FAX was minus 1.05 Newton, but you shouldn't take into account the negative sign because we have put it only to show the direction. So the value is 1.05 kilonewton and FDX is 0.242 F. So this is minus 0.242 F is FDX and FAX was 1.05 kilonewtons, and this is in Newton, equal to 0. So this is our first equation. So I'll just mention this as first equation. Now we'll apply summation of force in y equal to 0, upward as positive, assuming. So we have, let's say we go to this diagram this time. So this is ROY, we have FAY, we have FBY, and we have FDY. So ROY, FAY, FBY are positive and FDY is negative. So ROY plus FAY plus FBY minus FDY equals to 0. So from this again ROY plus FAY is 4 kilonewton plus FBY, which is unknown, minus FDY, which is 0.242 F, is equal to 0. So this is our second equation. Let's apply summation of force in Z equals 0. In this direction we are assuming positive. So we have ROZ. Let's go back and check. We have ROZ. FAZ is in negative. FBZ is positive. FDZ is positive. So only FAZ is negative. Minus FAZ plus FBZ plus FDZ equals to 0. So ROZ minus FAZ is equivalent to 1.47 kilonewtons minus plus FBZ, which is unknown, plus FDZ, which is 0.94 F newtons, is equal to 0. So this is our third equation. So now we have 3 equations done. Let's start with the moment equation. So summation of moment, we need to take it at a location where we have the most number of unknowns. So if you look over here, the most number of unknowns are located at point O. We have ROX, ROY, ROZ, three unknowns. Well, at RB, we have only two unknowns. So it's better to cancel out more number of unknowns by taking moment at that location. So moment about O, counterclockwise positive. Okay, uh, this is at O. Summation of moment in x direction, let's say, equals to 0. So if you are doing this, we can find out that the equation would be minus max plus mdx is equal to 0. So let's go back and confirm this. We have max, which is clockwise, so we put it as negative, and mdx, which is counterclockwise, which is positive. The same goes in these figures as well. So along x-axis, the moment is max and mdx only. This is negative and this is positive. Hence, I have written this equation. So this is equation number 4. And we already know the value of max. We found it as 1000. We know mdx is 0.94 times 187.5 times f. So we can determine what is f using equation 4. So we will leave it for now. We will go back and solve all these equations. But let's continue with the moment along the y-axis at O. Counterclockwise positive is equal to 0. So now looking at the y-axis, we have MAY and we have the moment that will be caused due to along the y-axis we have this force times the perpendicular distance, and also we have, which other force do we have? Let's find out. So along y-axis we have FAZ, FAY times 550, because that is from the force here. So this will have a moment actually the FAZ will have a moment about O in the y-axis. Yes, and even the FDZ will cause a moment about O. So FAZ is going to be counterclockwise, so it is positive, while FDZ is going to be clockwise, so it will be negative. So minus FDZ times the total distance is 1400. Okay, and also we have the RBZ, because the reaction at B will also cause a moment about the y-axis. So what was RBZ? We can write it as, since we are assuming the reaction to be positive, that is also going to be clockwise. So we will put it as negative RBZ times the distance, which is 550 plus 450, which is 1000, minus the MAY, which is only available in the y-axis. MAY. We don't have any other moment about y-axis from this free body diagram. So that is minus m ay equals to 0. So that is equation number 5. And now let's take moment about z at O equals to 0, keeping counterclockwise as positive. So now we have Fay, which is this force that would create a moment about z-axis, and it is counterclockwise. So there will be 4 times, or Fay times the perpendicular distance, which is 550, and due to Fby, again we are assuming it's positive, so it should be counterclockwise as well. So plus Rby times 1000, and here we have Fdy, which is going to be clockwise, minus Fdy times 1400. And then let's see what are the moment in the z-axis. We have mdz. If we come back here in z-axis, we just have mdz. We don't have any other moment. So again, that moment mdz was counterclockwise. So it will be plus mdz equals to 0. So these are the 6 equations for which we can solve for the 6 unknowns. Okay, so now let's continue drawing the moment diagrams. So step 3, it is to draw the shear diagram, and step 4 would be to draw the moment diagram. So let's start with the shear diagram, and we will have a total of 3 shear diagrams due to the forces in x direction, y direction, and z direction. And we'll have 3 moment diagrams as well, and we are also asked to draw the torque diagram. So let's start by drawing, let's say, the force in y-axis first. So let's draw the shaft as a straight line as usual. Mark the axis as x and y. Since we are going to draw the force in y, I'll just put it as Fy, and the units are in kilonewtons. So once this is done, we'll mark the points O, A, B, and D. So this is O, A, B, and D. Okay, so now we need to check what was FOY or ROY. ROY is minus 2.09 kilonewton. So we have to draw a line in the negative axis, and this has a value 2.09. Now what was FAY? FAY was 4 kilonewtons, so it has to go up by 4 kilonewtons. So we go up and we come here. This is 1.91, which is minus 2.09 plus 4, which will be 1.91 plus. And then what do we have is RBY, and it is given as negative 0.538. So we need to subtract from here 0.538. So this would be the force, and this value is 1.37. And as you can see, RDY or FDY, it was about 1.37 negative. So we come back to 0. So this region was negative, so the moment diagram will have a negative slope. This one is positive, and this one is positive. So now I'm going to draw the moment diagram right below. because it is easier to have the normal or the shear diagram above and draw the moment diagram right below that. So step 4 would be to draw the bending moment diagram. Okay, so similar way we'll draw the axis, and then we are going to draw the moment about the z-axis. Now why is this z-axis? The force, the x-axis and y-axis, if you are choosing this for the shear diagram, the axis which is not present would be the direction of moment. This makes sense because the z is like coming out from this point. So any force would create a moment about z-axis. So if you draw the shear diagram for xy plane, the moment diagram would be for the z axis. So the area under this graph would give you the value of moment at point A. I'm just going to mark the locations again over here. So this is O, A, B and D. So the value at A would be 2.09 times the distance between 0 to A. 0 to A, I mean O to A is 550. So 550 times 2.09, and it should be a negative slope, so it should be below the axis. So let's mark a point. Let's mark a point somewhere below and connect this here. All right. Now we have 1.91, and the distance between A to B is 450. So if you multiply that, the value would be it is less than 1149.5. So although the value is positive, it has a lower magnitude. So it will be below the point B. So it will be somewhere here, and the value here is 290. The value over here was 1149.5. And now what do we have? We have 1.37 times 400. So that has to go to the positive axis. So the value is greater than 290, and it is about here. So minus 290 plus the value that you obtain by multiplying 1.37 times 400 would come out to be around 258, which is going to bring the force down. Now, how did this come back to zero? We had, if you remember in the free body diagram, we had the moment in z mdz, right? So this mdz had a value of 256.8, which is almost close to 258. So maybe it is due to some minor calculation errors that it wasn't the exact value, but it should be close. So these two values are close enough, and we know that mdz was actually clockwise. So that means it is in the negative direction. So you are going to apply the clockwise and negative direction, which brings it back to 0. So this is the moment diagram, the first one that we have for when we drew the shear diagram with force in Y. So shear diagram is basically the let's say the normal force to the x-axis. So that's why we have drawn the Y force for now. Now I'm going to draw the second figure with Z as the on the top and X on the right. So we'll take another page. So now I'm going to draw the shear diagram but with respect to Z. So this will be Fz kilonewtons, and we have the x-axis. We'll just mark the points again, O, A, B, and D. This is O, A, B, and D. And we'll check what is ROZ. ROZ is 3.09 and it is positive. So the figure would be up, and this value is 3.06 kilonewtons. Then FAZ actually is minus 1.47. So we need to go down from here by 1.47. So that will be somewhere here. Draw a straight line, and this value is 1.59. And now we need to find what was RBZ. It was minus 6.92 kilonewton. So that has to go all the way down. So let's bring it down. And this value is about 5.33. And as you can see, FDZ is 5.33 kilonewton positive. So it has to go back up. So this was going to have a positive slope, and negative slope in the moment diagram. So now let's draw the moment diagram. And this time the moment would be about which axis is missing here? Y. So My, again the same way, 3.06 times 550 in the positive axis. So let's mark the points again. O, A, B, and D. So at A it is at around 1683 is the value. So we join this. Now before continuing, we need to check if there is any external moment. So external moment we can check from the free body diagram. So let's say if we look at the moment in Y, do we have any moment in Y? Yes, we have a clockwise moment MAY. And what is the value of MAY? We found it as 262.5. So let's go back here. We need to subtract that value from here. So that would be 262.5 should be subtracted from 1683. So we just bring it down as well. Okay. So if there is an external moment applied, you will draw the initial point and then you will draw either upward or downward depending on the direction of the external moment. So that is where it ends at point A. The point A has a maximum value of 1683, but with the external moment applied, it will be lower by 262.5. Now let's calculate the value at point B. So that would be 1.59 times 450. So 1.59 times 450, uh, that value should be added to this value and represented here because again it is a positive slope. So the value would be about 2132. The value would have been somewhere here if this was the point. But since we have an external moment, we have moved down, and hence the next value is with respect to the bottom point, because again the moment diagram would be a continuous diagram, so we have to go as per the loads that are applied. Now the last area is 5.33 times 400, and that is negative, and it ends at 0. So this is the moment diagram about the y-axis. Now we'll continue to the last axis. Draw the force in x diagram. So let's mark this as x, and we can mark this either as y or z. So I'll just put it as z, f of x diagram, and the units is kilonewtons again. Let's mark the points O, A, B, and D. So now what is ROX? It is 2.42, but it is positive actually. Some mistake here. Okay, so 2.42 in the positive axis. So let's put that here, 2.42. Now FAX is minus 1.05. So 2.42 minus 1.05 is 1.37. This is 1.37. And do we have RBX? No, because the bearing at B does not have any axial load. So there is no positive or negative force here in x direction. So it will continue all the way till D. And FDX is minus 1.37. So it will go back to 0. So I'm going to continue this line and go to 0. This is positive, positive, and positive. So this is the force in X diagram. Now we are asked to draw the torque diagram. So how do we draw the torque diagram? It is basically the moment about X diagram. Um, so how we do that is it would be moment of X is equal to the torque diagram, and let's mark the points O, A, B, and D. So in this case, the moment about X diagram, we have to look at the free body diagram that we initially drew. Where all do we have moment about x-axis? So we actually have MAX, which is this one, and it is clockwise, and we have MDX, which is applied, and which is this way. So which is counterclockwise. So we have a clockwise and counterclockwise moment, and it's applied at A and applied at D. We do not have any other moment on the x-axis. So these moments cause or lead to the torque in the system. So let's draw this in the diagram. So at A, we said the moment is clockwise, so it is negative, and it has a value of 1000. As you can see, MDX is 1000 and MAX is 1000. But MAX was clockwise, MDX is counterclockwise. So it goes straight and it goes back to 0 at MD of X. So the moment is negative, and this is the torque diagram that is required.